This is conceptual understanding exercises from Chapter 6, and we're going to do 21 all the way through the end of this PowerPoint, or all the way in through the end of your packet. And you have a 6 Newton falling object encounters 6 Newtons of air resistance. They want to know what is the magnitude of the net force. So let's go ahead and draw our object. Here's our object. The 6 Newton falling object would have a weight of 6 Newtons, and then there would be a 6 Newton air resistance going in the opposite direction. So you can see that they both cancel, and the answer would be 0 newtons. For number 22, number 22 says a girl pulls on a 10-kilogram wagon with a constant force of 20 newtons. So here she is, she's got her hair here, and she's pulling on this wagon with a constant force in this direction of 20 newtons. They want to know what is the wagon's acceleration. We know that force is equal to mass times acceleration. We're pulling on it with a force of 20. We don't know what the mass is, but we know, we do know what the mass is. Mass here is 10 kilograms, and we're looking for the acceleration, so we're just not really sure what that acceleration will be. If I take 20 divided by 10, I end up with an acceleration of the wagon of 2 meters per second squared. Watch out for that squared. Lots of people tend to miss it. Number 23, an object has a constant mass. A constant force on the object will produce a constant, and here this one is just acceleration. We know that if I have F equals ma, if this is constant and this is constant, then the a cannot change either. Number 24. Number 24 says if you pull horizontally on a desk, that means that we are pulling in this direction with a force of 150 newtons, and it doesn't move. The friction force in this direction, so this is the force of friction, has got to also be 150 newtons. Now it says if I pull with 250 newtons, so I've got 250 newtons of force that I am pulling with, so I'm going to put FP for pull. It says it slides at a constant velocity. Well, even though it's sliding at a constant velocity, the force of friction on the other side is going to be exactly the same, 250 newtons, because there is no acceleration, but it does have a constant speed. That is number 24. Let's go ahead and go to number 25. Number 25 says a box is dragged without acceleration. Here we can go ahead and say that A is equal to 0 in a straight line path across a level surface by a force, so we're pulling it with a force equal to 13 newtons. They want to know what is the frictional force. Well, we said that if it doesn't accelerate, the net forces have to be equal to 0, so our friction force here also is 13 newtons. For number 26, this will be the next question, it says a block is at rest on an incline. So let's go ahead and draw our incline, and we've got our box here. It says the force of friction necessary to prevent the block from sliding increases when the angle here is increased. So if I make this angle a little bit bigger, if you think about if you had a box on a ramp and you made it bigger, that force of friction that it pushing it up the other side has got to be bigger when you have the incline, and that's because you end up having gravity be just a little bit bigger as it goes through. Number 27. Number 27 says suppose the force of friction on a sliding object is 25 newtons. The force needed to maintain a constant velocity. So we've got the force of friction going in this direction. So that would be FF. It's equal to 25 newtons. If I want it to go in this direction with a constant speed, my forces have to be the same. So it would also be 25 newtons. It's got to be exactly the same for it to maintain a constant velocity. Number 28. Number 28 says you are on a frozen pond and the ice starts to crack. If you lie down in the ice and begin to crawl, all this will do, if you remember, pressure is equal to force per unit area. If I lie down, then what happens is my force is still the same. Let's say that I'm 100 newtons. If my area before was 20 square meters, and now I have a pressure to begin with of 5, then if I take that same force and I increase the area, let's say that this is 100 newtons, and on the bottom instead now I have a bigger area, let's say it goes all the way up to 50 square meters, I end up with a pressure of 2 pascals instead of 5. So this will reduce the pressure, and that's really the answer. So reduce pressure. Number 29. For number 29, it says, which of the following would exert the most pressure on the ground? And when you actually look at this one, it would be a woman standing not in running shoes, because running shoes, if you think about the bottom, running shoes kind of look like this. They have a lot of area here. If she's standing on skis, that would also have a lot of area. It's just a little bit longer. But if she was standing in high heels, you'd just have a little point. And that would hurt if she stomped on you. If she stomped on you in skis, it wouldn't be too bad, and with running shoes, it'd be a little bit worse than skis probably. But if she stomped on you with that pointed into that heel, that would not be fun. Number 30. Number 30 says, when a woman stands with 2 feet on a scale, the scale reads 280 newtons. If she lifts 1 foot, the scale will still read 280 newtons, because all of her weight is on that scale. So if she's standing with both feet on the scale, so there's a scale, it'll read 280. If she stands on the scale, we better give her some arms here. If she stands on the scale, and this time she does it with 1 foot up and the other foot on the scale itself, she'll still read 280, because all of that force is still pushing down. The pressure will be higher on this foot than it would have been on these two, but it says the scale will read 280 newtons. It will not change. Number 31. Number 31 says pressure, basically here, is just defined as force per unit area, and we've done that equation before. Number 32. Number 32 says the unit of pressure is, well, there's a couple ways to do it. We know that the ultimate unit is the Pascal, and that is equal to a Newton per meter squared. Same thing. Number 33. Number 33 says Aunt Minnie throws a rock downward, and air resistance is negligible. That means that we don't have to worry about air resistance at all. So we're just going to cross off the air resistance. We know that the rock has been thrown down this way. Compared to a rock that is dropped, the acceleration of the rock after it's thrown, and this is a trick question, it doesn't matter. The acceleration is always that of gravity. So whether I throw it down or I just drop it, the acceleration will be 9.8, or it'll basically just be equal to whether I throw it down or drop it. It's going to be the same. So the acceleration will be the same. Number 34. Number 34 says rock is thrown vertically into the air. So this rock, this rock right here, we have it being thrown up into the air. So it goes up, and it says at the very top of the path, the force on it is mg. So it's basically just its weight. Still has a force pulling it down. That force is mg. If there was no force pulling it down, it would just go into outer space. So there's got to be a force pulling it down. Number 35, a 10 kilogram brick and a 1 kilogram book are dropped in a vacuum. The force of gravity is on the 10 kilogram brick here is 10 times that of the book. And here's why. We know that force is equal to 10 times 10, so that would be 100 newtons. And the force on the book, its mass is 1, but remember gravity, the value for gravity is 10. So when you multiply those two together, it's 10 newtons. So this would be 10 times the force of the book. So 10 times the force of the book is your answer. Next one is number 36. 36, an apple weighs 1 newton. The net force on the apple when it is in free fall. Now remember, when it's in free fall, the net force in free fall would be 1 newton. There is no air resistance in free fall. There's no air resistance in free fall. So that is why that one is 1 Newton. Number 37, a tennis ball. So there's tennis ball and a solid steel ball with the same diameter. Notice that they have the same diameter, are dropped at the same time. He wants to know which one has the greater force acting on it. It's got to be the steel ball. Why does the steel ball have a bigger force? Well, they both have force. You take both of the forces times gravity, but the mass of the steel ball is much bigger than the mass of the tennis ball. So it says the greater force has got to be acting on that steel ball, and it's because your mass is so much bigger. So we're going to actually make that a little bit bigger. Number 38 says the reason a tennis ball and a solid steel ball will accelerate at the same rate is because when you drop them, they both accelerate at gravity. So remember, gravity is an acceleration, not a force. Number 39 says when an object reaches its terminal velocity, its acceleration is equal to 0. And that's because the force pulling down on the parachutist, which is Fg, is the same as the force of the parachute pulling him up. And when the two forces are equal, we say that there is no acceleration. So the sum of the forces there is equal to 0. Number 40. The terminal speed for a person parachuting with a chute open, so this is how fast they fall, is 15 kilometers per hour. So it's not too fast, but you have to be careful when you land that you don't break a leg. Number 41. Number 41 says a 20 Newton, so here's a 20 Newton object, encounters 4 newtons of air resistance. The magnitude of the net force on the object. So this 20 Newton object, we know it's 20 newtons in weight, encounters a force pulling it up, so the air is pushing it up with 4. If I just subtract the two, I'm going to take 20 minus 4, I end up with a 16 Newton force pulling it down. So we would say this is down. Needs to have a direction. So 16 newtons in the downward direction. Number 42, a heavy person and a light person parachute together and wear the same size parachute. So you'll notice 2 parachutes are the same, but this person is much larger than this person. Assuming they open the parachutes at the same time, which one reaches the ground first? Well, this one's going to have a bigger force pulling down than this one because this person is smaller, but the force of the air resistance for each one is exactly the same. And so because the person that has the bigger mass has a bigger force in the down direction, they will hit the ground first. This one hits the ground first, so the heavier person will hit the ground first. Number 43 says as a care package, so you'll notice these are care packages that are getting dropped out of the helicopter. As the care package falls from a high-flying stationary helicopter, its velocity increases and its acceleration. Remember, even though the speed gets higher, so right here might be falling at 10, here it's falling at 20, and on the ground it would be falling at 30 meters per second. Acceleration for each one of these is just 10, because we said that gravity is just 10 meters per second squared. Number 44, this is the last one, a tennis ball and a solid steel ball with the same diameter dropped at the same time. In the absence of air resistance, which ball has a greater acceleration? Neither. They both have the same acceleration. Both of them have an acceleration equal to gravity. They don't have the same force. This one has more force, but they both fall with the same acceleration. So this one would be exactly the same. And that is the end of Chapter 6, Conceptual.